There are a couple of magic tools that we can rely on when it comes to celestial navigation math. As the saying goes, we stand on the shoulders of giants. In this film, I'd like to talk about some of the magic tools such as HO229 and how we can use this to help make our site reduction process easier. In this step, we'll take the information we deduced in the last step when we built a triangle, and we'll feed it into this magic tool so that we get some output from it. So in the last step of this process, we built a triangle. Let's just do a quick review of the things that we've learned since then. Let's imagine that this is the equator. And this is the northern hemisphere, and here's the North Pole. In the last step, we built a triangle, and we established the elevated pole, or the pole that's closest to us in the hemisphere, as well as the geographic position of the object in the sky that we were interested in. Finally, the third point on the triangle was our dead reckoning position, or our assumed position, the position we did a little bit of math to allow us to create a nice triangle. What we want to do when we have this triangle built is feed that triangle into a tool such as HO229 or a formula that you've got memorized. This book is a book that's going to spit out solutions to a triangle. So if you remember from grammar school or middle school, if you know two legs and a corner or an angle of the triangle, you can calculate all the rest. So let's take stock of what we know. Well, we know the geographic position of the body in terms of its declination, or its distance north or south of the equator. Obviously, though, this is different. It turns out 90 minus the declination is equal to the co-declination, this leg of the triangle. So that's 1. We also know our assumed position from the last step in terms of its latitude and its longitude. Again, the latitude is not relevant in this case, but the co-latitude, or 90 minus the latitude, is. And then finally, we determined the LHA, the local hour angle. So if you take stock of this, we've got a leg, and an angle. If we feed that into this book, it's going to spit out all the rest. So once we feed the information into HO229, we give it whole values of declination, latitude, LHA, and it spits back some results. The essence of what we're going to use this information to do is kind of as follows. So if we know the geographic position of the sun at that point right there, that's going to be a great milestone to use. We also kind of picked a position earlier, and we said that this was our assumed position. So when HO229 gives us some results, it really gives us two things. The first is an azimuth, or in essence, the angle of this corner of the triangle. Specifically to celestial navigation, since we're doing spherical triangles, it's technically this angle right there. That's the direction to the sun, or the GP of the object. The second thing that it gives us is it says that we assumed that we were right here when we made the observation, and therefore the sun should be some certain height above the horizon, maybe this right here. Well, if you were closer to the sun than the assumed position, the sun's going to appear higher in the sky. If you were further away from the sun than the assumed position, the sun's going to appear lower in the sky. And so given that we have an observation, we can take the computed value, the observed value, calculate the difference, and plot the intercept on a human-sized chart. So now that we've talked a little bit about how HO229 can help us, let's go back to the dry erase board and take a look at how to solve these type of problems using some actual examples. HO229 is one of the key tools for solving navigational triangles. There are other uses of it, of course, but our primary focus is going to be on solving the navigational triangles using the arguments we arrived at in step 3 in this 4th step. So this is the site reduction tables for marine navigation. The standard test version is latitudes 15 to 30, but it is a series of 6 volumes, 0 to 15, 15 to 30, etc., all the way up to 90 degrees. This is the commercial version of the publications. So right away on the inside of the pub, there is an interpolation table. This interpolation table is used later in the process. There's one at the front and one at the back of the book. Diving into it a little bit further, there is a table of contents and some introductory material, which is actually really, really good stuff. So in your studies of marine navigation and celestial navigation particularly, it is definitely worth reviewing some of this stuff. Also wanted to point out that there are some really nuanced corrections that we'll get into a little bit in this course, and then you can find some more detailed information here in the front matter, specifically to what's called double second differences. But the majority of the book is made up of pages of numbers, which are beautiful, and there are kind of a few key things to look at. Number one is that the pages are listed by LHA, local hour angle. So you determined the whole value of LHA in the previous step, and they're listed whole values here. Just note though that there are multiple LHAs per page, and that they are also located at the bottom of the page in some regards there as well. So triangles are triangles whether they're on one side of the earth or another. So in order to save space in the tables, they can be repeated. There's also declination along the left side in whole numbers, and then latitude along the top and the bottom in whole numbers as well. Of note, this is the volume from 15 to 30. So the second half of the book, way back here, is going to have the second half of the latitudes. So if you get confused as to finding a latitude that you think should be there but is not, look in the other part of the book. So once you find a value, you can zoom in, and the book is going to give you, in essence, what's known as HC, or the height computed. So that's the height of the celestial object as if you were standing at the assumed position. The D, which is known as altitude difference, it's a correction factor that we'll get into a little bit later. And then Z, which is azimuth angle. This is not the exact bearing to the celestial object, but rather it's an intermediary value that's going to allow you to calculate the direct bearing to an object. So this is azimuth angle. You're ultimately going to be searching after azimuth itself. So there's a process to that, which we'll get into in a little bit. So HO229 is a great resource for solving these triangles. It's going to be the main focus of this step. Take a few moments to skim through it, whatever version you have, and then we'll carry on. The site reduction tables for air navigation is known as Pub number 249, published by the National Geospatial-Intelligence Agency. And this is a concise version of site reduction tables. It's meant for air navigation, as the title indicates, and specifically for fast-moving aircraft. It enables things to be done kind of quickly. For that very reason, a lot of mariners like to use HO249 instead of HO229 or direct calculation. Although this course does not focus on using the site reduction tables for air navigation, I will go through them quite quickly. In the front cover, there are some tables for corrections, for changing positions of the body and changing times for the vessel that's moving. There's a neat page for navigational stars. So the main navigational stars, given their visual magnitudes, their SHA, and their declination. Of note, this volume is based on an epoch of about 10 years. So every 10 years, you do need to replace portions of this table. Just like HO229, there are some excellent explanatory materials in the beginning. So as you dive into your studies of celestial navigation, certainly read these as you get some time and as you learn more and more about it. So the first thing you'll notice about the main pages of the Air Almanac, or the site reduction tables for air navigation, is that they are rotated 90 degrees. No real reason for that other than the way that the numbers fall. The difference here is that declination is listed for the main pages. All right, so you can see the changes in declination. Latitude is also listed for the main pages, so they're kind of listed by your latitude. So depending on your latitude, you can flip to a page and get all the data that you need there. So that's different than HO229. And then along the left and the right side are the LHA. So with HO229, the page is based on LHA, and HO249, the page is based on latitude and declination, and you look up the LHA that way. You will also notice the values in here for declination along the top, and then just like HO229, the three values that we pull are going to be HC for height computed, D for altitude angle, Z for azimuth angle. So those will be corrected in the normal way, just like HO229. Towards the back of HO249, there are some additional tables. So there's GHA and declination for the suns for certain epochs. There are GHA data down here as well, and then some corrections in there. So if you are interested in HO249, get yourself a copy. You can download it off the internet with the links provided, and you can use that to supplement your study of celestial navigation. This course focuses mostly on HO229, instead, but this is a valuable tool that you can use to expand your celestial navigation knowledge. So the process of using HO229 to solve celestial triangles is generally the same for any celestial body. In step 3 of the process, remember we paid particular attention to finding values for 3 key metrics. The first was LHA, or local hour angle, in whole numbers. The second was declination, also in whole numbers. This is for the GP of the sun, or the celestial body. Finally, there was latitude. We rounded to the nearest whole latitude for our assumed position. These 3 values allow us to go into HO229 to pull out values. The values that we're going to pull out are HC, which is the computed height of an object as if you were standing at the assumed position. D, which is a correction factor known as altitude difference, which is used to refine the solution of the triangle. In essence, it's going to help us account for the leftover declination. We'll get to that a little bit later. And then finally, Z, the azimuth angle of the navigational triangle. This is an intermediary value. It's not the final solution, but again, it will help us get to where we want to go. So given these factors as an example, let's go find them in HO229. So HO229 is organized best by LHA. So the first thing we'll do is flip to the page for an LHA of 30. So the LHA is located at the top and the bottom of pages. And then also the triangles are, somewhat malleable. A triangle is a triangle, so you might get some different numbers even though it's the same kind of triangle that you're solving. But up here the LHA is 30, so we've got our first metric. The second metric would be our latitude that we'll look at. So this part of the book is 15 to 22, and then later in the book there's also a page for LHA of 30 with latitudes 23 to 30. So it's important to know where in the book you are. So we've got LHA of 30, we've got latitude of 15. The last step is to pull the declination. So the declination here is 10 degrees. So we look in the 10 degree column and we're going to pull these 3 values. So our height computed should be 60 degrees, 18.8. Our D, or altitude difference, is plus 12.4. And our Z, our azimuth angle, is 96.1. So that would be an example of how to pull these values out of HO229. So what you would do as part of the step 4 of this process is you would write down these values. So our HC, we said, was 60 degrees and 18.8 minutes. Our D number is 12.4. That's our altitude difference. And our Z was 96.1 degrees. So what's going to happen next? HC is going to stand for the height that you should have seen this object at if you were standing at the assumed position. You're not, so there's going to be some corrections that need to be made later in step 5. However, in step 4, we will correct these 2 values here. So D is the altitude difference. It's going to help you account for the rate of change of altitude from declination to declination, and in essence it'll account for any leftover declination that we didn't account for already. Finally, the Z, the altitude difference, is going to help us when the celestial triangle, if this is our AP and this is our GP, it's going to help us get the bearing from AP to GP exactly. So we'll refine that a little bit as well. So in the next series of steps, we're going to focus on the altitude difference and the azimuth, and then we'll be able to kind of bring it all together to solve these triangles for various celestial objects. Often when we deal with celestial navigation and tables, we have to make little corrections and little nuances, and that's half the fun and half the battle of all this. So I wanted to zoom out for a minute and just remind you of the navigational triangle. There's an elevated pole, there's a geographic position, and there's an assumed position. Ultimately, we're interested in refining this assumed position and plotting on a human scale chart. So when we solve these celestial triangles, we're giving it 2 sides and an included angle, or LHA, and asking it to solve all the rest of it. But a triangle is the same whether you kind of rotate it or put it in an opposite hemisphere, or just kind of invert it in any way. A triangle is still a triangle. So the tables are not infinitely thick. They're quite big, but they could be bigger if they listed every single triangle. Instead, they ask us to make some adjustments. And one of those adjustments deals with kind of this angle right here, which is known as Z and eventually going to be Zn. So if we were to zoom into a more human scale size chart of the assumed position, you might say that the North Pole is straight up and the direction to the GP from the assumed position is kind of like that. We ultimately want to know really what this angle is right here. This is a compass angle, a degrees true that we could just measure off our compass or put on a chart, and then we could take our dividers and our parallel plotters and we could actually plot that on a real chart. So unfortunately, the tables don't give you that angle directly. They're going to give you instead Z, which is your azimuth angle. And they're going to ask you to convert it to Zn, which is your azimuth. So this right here is what we want. That's our Zn. So what do the tables actually give you? The tables are going to typically give you an angle from north deflected to the east or to the west, right? So this is similar to other areas of celestial navigation, which you may or may not have dealt with, but it's a notation that kind of references the geographic pole that's in your hemisphere and then deflects it to the west or to the east. So in this case, they're actually giving you this angle, which is your Z. So that's what the solution to the triangle in HO 229 is going to give you. And there's a set of rules that will allow you to convert this into a real measurable degrees true that you can plot onto a chart. Those rules can be found on really any page in HO 229. They're located near the center margin at the top and at the bottom. So these are the azimuth rules. So we'll zoom in on them. They're also typed out into the course material. But in essence, first you think about what hemisphere you're in. So if you're in the northern latitude, you have two options. If the LHA is greater than 180, well, the Zn is just going to be equivalent to your Z value. So you pull a Z value from this book, that's going to be your actual angle if your LHA is greater than 180 and you're in the northern hemisphere. If you're in the northern hemisphere and the LHA is less than 180, you have to subtract the value that you pull from 360 to get your actual Z. So that kind of reflects the drawing that I just made for the northern hemisphere. In the southern hemisphere, the rules are similar, just a little different, just like everything in the southern hemisphere. So if you're in southern latitudes and the LHA is greater than 180, then the Zn is going to equal 180 minus Z. And if it's less than 180, the Zn will equal 180 plus Z. So these azimuth rules can be applied to really any problem that you're working on. So you can say have an LHA, a latitude, and a Z value that you've obtained in the previous step and just need to apply some corrections to it. So if our Z value, our azimuth angle, was 127 degrees, that's not our final answer. It's really just referenced from the given latitude in an east or a west direction, depending on how the triangle is formed. We need to convert that to a Zn, something that we can actually plot on a chart. So the rule in this case is if we're in the northern hemisphere and the LHA is greater than 180, then Zn is equal to Z. If it's less than 180, like it is in this case, we need to say Zn is going to be equal to 360 minus Z. So Z is 127. So our true correction, our Zn will be 360 minus 127, or 233 degrees. So if we had a human scale chart, we could pick our assumed position and then use our dividers or our triangles or something to measure a bearing of 233. Right, so this would be north, this would be 233 degrees, and allow us to plot this on a chart. So in step 5, that'll be really important. But the key factor for this video is making sure that we can convert a Z value from the table to a Zn value, an azimuth angle to an azimuth, using the 4 rules that are given in HO 229. In step 3 of our process, we got pretty good at taking a declination for any celestial object and then using the whole value of it only to allow us to use HO 229. But we always have to account for this remainder. This is known as declination increments. So for example, if our declination was 12 degrees 32.6, it's really like 12.5 degrees. And if you ignore that half a degree, you're going to have your solution offset by, ever so much that it could make a difference. So in step 4 of the process, we're going to use a value known as D, altitude difference. And I fully recognize we've already introduced a small d in another category when we talked about declination, but such is life in celestial navigation. This will help us account for this leftover declination increment. When we pull values of h, c, d, and z for any specific site that we're working on, the d value is known as altitude difference. It's given by a plus or a minus sign, and it represents the change in hc from declination value to declination value. So for example, from the declination of 0 to 1, there is a change between these HCs. So the altitude difference will help us account for anything in between 0 and 1 along those lines. Of note, the altitude difference value does change in sign from positive to negative, and so you should account for that when you're doing your correction. Additionally, there are occasionally places in HO 229 where the altitude difference is written in italics and it has a little dot next to it, sometimes represented by a star, depending which version you're using. This indicates kind of a complex phenomenon that's rarely important in our calculations, but we will talk about it. It's called a double second difference. So more on that later. Typically, when we retrieve values from HO 229, we get an HC, or a height computed, the height at which the object should be if you were standing at the assumed position, which we rarely are, D, which is an altitude difference, and Z, which is the azimuth angle, which we've previously learned how to convert to ZN. In this section, we want to take this altitude difference and help us correct this HC value ever so slightly. So there's two ways to do it. The first way is to use direct calculation, which is by far the simplest way. The second way to do it is to use the interpolation tables in HO 229. Either way, whether you're using direct calculation or the interpolation tables, they're written the same way. The correction that you're going to apply is equal to the altitude difference, the little d number that we just pulled from the book, times the declination increment, whatever's left over from step 3, divided by 60 minutes. That's going to result in a plus or a minus correction, which is applied to the HC value to help us dial in our site ever so slightly. As an example, if the declination increment left over from step 3 was 12.5, for example, if the declination was like 10 degrees, 12.5, we already used the whole value. Now we got to account for the declination increment. The D value that we pull from the book, let's say it was plus 49.9, we're going to get a correction. So we'll just say 49.9, usually we'll call it plus, times 12.5 minutes over 60 minutes is going to equal our correction. And if we throw that into a calculator, it's going to be 10.4 minutes of correction that we'll add to the HC value. We'll learn about that part a little bit later. But obtaining this correction is the focus of this video. So using the direct calculations is probably the easiest way to do it. However, if we wanted to use the interpolation tables from HO 229, we can definitely do that as well. The way these will work is in the front and the back of HO 229, there are these interpolation tables. The declination increments are listed along the left side. So your first step is to find the declination increment, which was 12.5 in this case. So here's 12.5 for the declination increment. So let's zoom in a little bit. All right, so here's 12.5 for the declination increment. The rest of the table here allows you to correct for things. So if we kind of look up at the top, this is the altitude difference, the D. The way that they chose to do this is they break the altitude difference into tens and units and decimals. So for example, our D number was 49.9. You can think of that as 40 and then 9.9. right? And so what you'll end up doing is you'll use the area which is closest to your declination increment, 12.5. So for the units value, it was 40 units. So that's 8.3. So 8.3, and we'll note that value. And then over here, in the area closest to the 12.5 declination increment, we'll pull the remainder of 9.9. So as a reminder, here's 9, and we'll just scroll down. So it's 2.0 there, and 9.9 is 0.2. So we've got 8.3 plus 2.0 plus 0.2, which should equal our correction of 10.4 or thereabouts. So either way, you get the same result by using the interpolation tables or the direct calculations. To me, my strong recommendation is to use the direct calculation. It's quick and it's, not subject to misreading numbers in here. It also allows you to think a little bit more. The one advantage to the interpolation tables is if we do get into the double second difference category. And so these are areas where we're going to correct very few sites, and those are generally only if the site is high altitude. So if it's above 60 degrees, there might be some changes that we need to make here. So I've included an example in the written portion of the course, and there may be subsequent material available to you as well. But since it is a rare occurrence, I'll just leave you with the fact that there is an excellent explanation in the first part of HO 229, specifically regarding the non-linearity of the tables. In essence, the tables don't increase linearly as you get to high altitudes, and you just need to make a little correction for it. The correction is typically very small. Again, it's called a double second difference. It's located in the margins of here in the interpolation tables, and you can check that out in the written portion of the course or dive into it if you're interested in that level of precision. This video will be supplemental material. It deals with what's known as a double second difference. It's a very minor correction, but in the interest of completeness, I do want to include it in the course. So let's say, for example, you previously had a declination of your GP of 13 degrees 24.2. This was the whole value that you took into HO 229, and you obtained a D number of plus 28.7 dot. This dot indicates that we need to apply a double second difference. What's going on there is, in essence, when you take a sighting of a celestial object, if it's low to the horizon, or really up to about 60 degrees, things change typically linearly in the tables. But as the sight gets higher and higher, the tables themselves change and they are non-linear. So you can't just look in the table and pull a value and assume that it's going to change at a known rate. Instead, there's changes to the changes, right? And so it's kind of like acceleration versus speed. So it's just a second order issue that we need to deal with. It's typically very small, but we want to take a look at it anyway. So in the case of this example, let's say you pulled a D value of plus 28.7 dot for a whole value of declination of 13. You also got an HC and a Z, and those are dealt with elsewhere. The first step is going to apply the normal kind of linear correction that we've already dealt with. So all we really need to do is apply the normal formula of D times dec inc over 60 to get our value. So the D was plus 28.7. The dec inc was 24.2 from up here, divided by 60. And if we throw all that into a calculator, we will get a value of 11.6 minutes. And so that's an added value of 11.6 minutes. So that's the regular, normal linear interpolation of this 28.7. However, the non-linearity of it for the double second difference requires us to kind of dig into the tables a little bit. So in this case, this is maybe the page we were using. Here's the 28.7 dot that we were interested in. What we need to do is note the value above it and below it. So the value above it or immediately preceding it is plus 30.6. All right, so here's the 28.7 dot. 30.6 immediately precedes it, and 20 6.6 is immediately following it. They're all plus, and when we do double second differences, they are always added. So the rule goes as follows. You need to subtract the d value immediately prior to the desired d value from the d value immediately following it. So in essence, we'll take the plus 26.6, which is the value immediately following, and we'll subtract a plus 30.6, which is the value immediately preceding. We'll subtract the following from the preceding, and we end up with a value of negative 4.0 for our first factor. So what we can do then is we can dive into the interpolation tables in HO 229. All right, so the first thing would be to find the declination increment, which we said was 24.2. So here's 24.0, here's 24.2. So we'll zoom in a little bit. And what we'll end up doing is we'll stay in this vicinity. We're going to go over to the double second difference category, which is closest to the value that we've got in question. And then we're going to use this almost like it's a dip table from the Nautical Almanac. Along the left are bracketing values. You find where yours falls in there, and then you apply the correction listed here. So we said that our factor was negative 4.0, which is going to fall between the 2.5 and the 4.1. So our correction is going to be a 0.2, which is always added. So regardless of the sign, the double second difference is always added. So again, we look for the declination increment. We stay in that vicinity to find the double second difference correction. We use it almost like a dip table. So on the left side, we look for bracketing values for the number that we previously calculated. So 2.5 to 4.1, and then we pull a correction, in that case of 0.2. So this is a plus 0.2 correction, and is going to account for the non-linearity of the tables themselves. So we took the following, subtracted the preceding, got this value, and then entered the tables with it. These two get added together, so it's 11.8, and that's our total correction. So as you can see, this double second difference is usually a pretty small correction, but you know, it's a quarter of a mile. So if we're doing this for extreme precision, it is worth doing that, especially for these higher altitude sites. So you can dive into HO 229 for a reading of the materials in the front of the book for a little bit more detail on this double second difference correction, and carry it in your toolbox going forward. The key skill for this section of the celestial site reduction process is going to be retrieving data from HO 229 and in essence solving that celestial triangle. So let's dive in and look at that in a little bit more detail. So we know how to generate an LHA, we know how to pick a whole value of latitude for our assumed latitude, and we know how to pick a declination as well, using the whole value of it to go into HO 229 and deal with the declination increment later. So let's take a look at the publication and see what we can pull out. Given the site reduction tables for marine navigation and an LHA, a latitude, and a declination, remember that the pages are governed by LHAs, the latitudes are across the top, the declinations are across the side. The book is broken into 2 volumes, so the first half of latitudes are in the front half of the book, the second half of latitudes are in the back. So our LHA was 30 and our latitude was 15. So we'll be in the front of the book, we'll look for an LHA of 30, which we've got here, LHA 30, LHA 30. Our latitude is 15 degrees north, so we've got that column, and our declination is 10. The last thing to decide is, are we on the same or the contrary pages? Since the latitude and the declination are the same hemisphere, we're going to be on the same page over here. So we can look in here for a latitude of 15, a declination of 10, and an LHA of 30, and we'll pull out our values for our height computed, our D value, or our altitude correction factor, and our Z, or our azimuth angle. And then we'll go back to the whiteboard to correct all these. So having pulled data from HO 229, we have a computed height, a D number, altitude difference, and a Z number, an azimuth angle of 96.1. We need to then work on these to refine them to our final answers. So let's start with azimuth. So in the northern hemisphere, the latitude, or the LHA rules rather, say that if LHA is less than 180, then your ZN is equal to 360 minus z. So this is a pretty easy one. In essence, all we need to do is take 360 minus 96.1, and we can get our true Zn, or azimuth. So we can use a calculator for that one and say 360 minus 96.1 equals 263.9 degrees true. So that's what we're actually going to plot in the next step of the celestial process. Dealing with the height computed and the altitude difference is going to be our next step. So if we take the altitude difference and multiply it by the declination increment and divide the whole thing by 60, you'll end up with the correction that you need to make here to the height computed. So 12.4, and it's positive, times 12.7 over 60 is going to be our answer. So it ends up being 2.6 minutes that we need to add. So this right here goes over here, so plus 2.6 minutes, and now our computed height gets corrected as well. So 18.8 plus the 2.6 that we just accounted for equals 60 degrees, 21.4 minutes. So that's our computed value. And so we're going to take that into the next step, step 5 of the process, and compare that to our height observed. Then we're going to do some plotting. We're going to plot kind of the difference, and we're going to plot this azimuth, and we'll get to it when we get to it. But this is an overview of pulling the data that we learned about in step 3 into HO229, retrieving some data, and then correcting it to get our final solutions that we're going to take on to step 5. Although you don't need to know astronomy in order to do celestial navigation by following the steps that we've outlined in this course and using the tables, typically if you're interested in navigating celestially, you're also interested in the night sky. So I thought it might be helpful to talk a little bit about astronomy, particularly about the solar system and the general universe and galaxy, to help us put some of this learning into place. So starting with the solar system, we can assume that the sun is in the center of the solar system and that the Earth orbits around it. Now, celestially navigating, we actually think of it in a different way, that the Earth is the center of the universe and everything orbits around us, that tracks through the night sky. So scientifically, this is more accurate. Specifically, the Earth is going to revolve around the sun, and it's also going to rotate itself. So from a top-down perspective, the Earth is going to move in this direction around the sun in its revolution, and it's going to rotate around itself in this direction. So typically, if you're on the Earth, you might, rotate, and then you'll see the sun rise, and eventually the sun will kind of set once it moves away from your perspective there. There are two types of planets that we deal with celestial navigation. So there are planets closer to the sun than the Earth, and those are called inferior planets. So for example, we might have Venus. Venus is going to revolve around the sun in the same direction, but relative to us, we may see certain things happen. So for instance, when the Earth, Venus, and the sun are oriented like this, and it could be Mercury also, not something that we typically use for navigation, but for Venus's purposes, we are in conjunction right now, and we can't use Venus because it's blocked by the glare of the sun. Even though Venus is in front of the sun, it's just too bright to see. As Venus moves into a different position relative to Earth, it's at its what's known as maximum elongation away from the sun. And so if you were looking at a horizon and you maybe saw the sun setting, or the sun in maybe setting or something, Venus is going to be as far away from the sun as it gets in the course of a year when it's at maximum elongation. Later, Venus might pass behind the sun relative to us, and of course everything is moving relative to each other, but just for illustrating purposes. It's also at it's occulted, it's blocked by the sun in this case. And then finally, if Venus were over here, the situation would be a little bit different in that, Venus would be kind of setting when the sun still has a lot of distance to travel. It's maximum elongation in the other direction. So Venus is helpful to navigate with for a good portion of the year. And we call it either a morning star or an evening star, depending on whether we predominantly see it in the morning or the evening. Right here, you probably wouldn't even see it because the sun is so bright. So when it's an evening star, the sun sets first and then Venus sets second. When it's a morning star, Venus rises first and then the sun rises after that and obscures it. However, you can actually see Venus during the day if you know where to look. I got a really fantastic cross-bearing sight with the sun and Venus one time when I was out in the Pacific. So you just have to look really carefully. Sometimes you can see it during the day. So these inferior planets kind of orbit the sun faster than the Earth does. And so they kind of lap us. And so over the course of the season, if you were to put the sun in an instantaneous position, you're going to see Venus over here. And then, over the course of the year, it's going to move to over here and back and forth. So this motion, this elongation in one direction or the other is all relative to how you view it in comparison to the sun. So inferior planets, Mercury and Venus, Venus being the predominant one that we would use for navigation, often not mistakable for anything else. It's generally close to the sun, either in the evening or the morning, very bright. If you look very closely, there's even phases of Venus, just like phases of the moon. So these planets are going to be exceptional for sighting, but they are typically close to the sun, particularly Mercury, which is very hard to see, and then Venus as a navigational planet. Just like there are inferior planets, the Venus and the Mercuries of our world, there are also superior planets. So if this is the sun and this is the Earth's orbit around the sun, revolving in that direction and rotating in this direction, if we're looking at it from the top, there are superior planets. These are the planets that are further out from the sun than us. We've got 3 navigational planets: Mars, Jupiter, and Saturn. There's also Uranus and Neptune, and then Pluto. If you're you think it's a planet, then great. But the 3 main ones we'll use for navigation are Jupiter, Mars, and Saturn. So we'll just represent it with Jupiter, kind of in this case. And so it's going to go around the sun in the same general pattern, but it's going to take longer than the Earth to do one orbit around the sun. So, but it will work in the same direction. And so when the planets are oriented in this way, we're at what's known as opposition. So the sun and Jupiter are on opposite sides of the Earth. So at midnight, you would see Jupiter highest in the sky for the day. So it's very brilliant. It's great to see. It's not super helpful for navigation because it is so high up in the sky and the horizon is typically obscured. But around, when Jupiter rises and sets, it should be a great time to view it. This is also a great time to view the moons of Jupiter. Typically, depending on where you're at on the planet, you're going to see up to 4 tiny little pinpricks, the Galilean moons of Io, Europa, Callisto, and Ganymede, orbiting Jupiter that Galileo saw through one of the first telescopes. Even through a set of binoculars, you can see this if you've got good vision. And then when Jupiter is behind the sun, it's obscured, it's occulted by the sun, you won't have it visible in that case. Luckily though, for us, Jupiter is visible in the night sky for a good portion of the year, other than when it's obscured by the sun due to the Earth's orbit around the sun as well. So it's typically viewable in the sky for a good portion of the year if you know where to look. Some of these planets do what's known as retrograde motion apparent to us. And so a good one to demonstrate that on is Mars, because it's relatively close to Earth. And if you can imagine, a few different positions of Mars as Earth kind of laps it in the sky. So if they're going around and Earth is going faster than Mars, if you were to look night by night at the horizon and plot the position of Mars relative to the background stars, it's going to kind of continue changing direction night by night and then slow down, reverse, and then pick that motion back up again. This is known as retrograde motion. And it was very, very hard for kind of the early astronomers to, explain. They had a lot of good models and a lot of good reasons for why things did certain things in the sky. And, when the sun-centered model came to pass, they could explain just about everything except retrograde motion. And actually what's happening there is that the Earth is passing the moon. So relative to the background stars that are out there, you're going to kind of see it in a few different positions, and it's going to cause this retrograde motion, typically once a year or once in orbit around the sun. So the superior planets have the benefit, there's 3 of them, they're brilliant, they're pretty hard to miss, they're always in the ecliptic, the same path that the sun traces through the sky. You can see Jupiter's moon sometimes, and in fact you can also calculate your longitude based on the eclipses of Jupiter's moons. That's a pretty nuanced thing that you can do, but old-timey sailors did that before the invention of the chronometer. But yeah, there's 3 of them out there in space that you can check out. Something's generally always visible at a different point in the night sky. So you can check out the Nautical Almanac for more on where these planets might be located at a particular time. But the main navigational planets of Venus, which is an inferior planet, and then Mars, Jupiter, and Saturn, which are superior planets, are going to make for excellent celestial navigation targets. When we think of stars and astronomy, there's a lot to it. You could spend a lifetime learning it, but I really think there's about 3 things that are critical to us as celestial navigators. The first is that the stars are very, very far away. So way out there in space, light years away, and you can consider the light rays from them as being parallel. So for you on one side of the Earth and me on the other side of the Earth, there's going to be no meaningful difference, specifically no angular difference that we'll notice when we're looking out at the stars. So they're far away, no parallax. Now, truthfully, this is kind of interesting, I think, that as the Earth orbits the sun, there's actually, a good bit of difference there, basically 2 astronomical units. And when stars are far away, you can actually do a little bit of this parallax. And this is going to be for astronomers, but we're talking about very, very small numbers. So it's not going to make a difference to us as celestial navigators. You can consider them far enough away that they are kind of infinitely far away, and parallel rays are going to shine from them. The second one is that stars are variably bright. So each one's going to have different brightness. And that brightness has to do with how close they are to us and how bright they are in general. So the word for this brightness is magnitude. And the Nautical Almanac has chosen a certain number of stars to represent on this left page over here. I think it's 57 navigational stars, and they're chosen based on their brightness or their magnitude and also their distribution throughout the sky. Later in the text, there are some star charts here to help you, find your way regarding these stars. So there's polar stars for the north and south, and there's equatorial stars near the equator, things to look at there. So these pages in the Nautical Almanac are fascinating, and they're very helpful when you're trying to find a star and choose what to observe. But these navigational stars, if you see any of them in the sky, they're all pretty much spread out throughout the sky at reasonable magnitudes that they're going to make exceptional targets for celestial navigation. So their brightness, or I guess let's term this magnitude, is important, but not necessarily specifically for navigation. It's just something to keep in mind. And the third is a little bit of kind of the history of navigation. For us on Earth, you can kind of consider everything being on a celestial sphere. So you can imagine that all the stars are basically infinitely far away, but on a sphere around us. Now, we know that the Earth orbits the sun, etc. So if you kind of combine these models, this is the Earth's orbit around the sun, and I know the sun is much bigger in real life, at least 3 times bigger. You can think about kind of how these stars are going to look from night to night. So number one, there's 360 degrees in our orbit around the celestial sphere, or the celestial sphere's orbit around us. There are 365 days in a year. So it's really about 1 degree per day that the stars are going to shift position relative to us. If we're looking out at these stars, they're going to shift position. So in essence, if you're looking out there at the horizon and you see a star, maybe Sirius, at a certain altitude, the next night, it's going to be just 1 degree different in the sky. So depending on the path that it takes or what hemisphere you're in, it's only going to be about 1 degree different. And so the fact that this is not very different from night to night makes it very convenient for us as we are navigating across an ocean. From night to night, we're going to be able to look up and see basically the same night sky, just shifted about 1 degree each night. Now, it's very important to note that planets are different. We'll talk about planets in a separate video, but the Greek word for planets is whatever it is, but it means wanderer. And so they're going to take a different path throughout the sky. And in essence, you can think about the planets on their own spheres. So there's the Mars sphere, the Saturn sphere, the Jupiter sphere, the celestial sphere, the moon sphere, the sun sphere. And so that was kind of the early indications of how celestial navigation worked with these spheres. However, we now understand more about orbits, but the celestial sphere is still one that's worth kind of remembering. So we'll call that the celestial sphere. So 3 things: they're very far away, they're variably bright, but they all have a magnitude, and the celestial sphere changes about 1 degree per night. Those are some factoids about star astronomy that I think are helpful to you as celestial navigators. So earlier in the course, we've talked a little bit about the moon and what's known as horizontal parallax. That's something that we used when we were using kind of the early steps of this process in the Nautical Almanac. I did want to take a chance to explain a little bit about the astronomy of the moon for us as celestial navigators trying to learn a little bit more about the subject. If the sun were, really, really big and the tiny little Earth is located out here, one thing that you can assume is all of the sun's rays are roughly parallel to everybody on Earth. So if you were to zoom in on the Earth, the sun is so big and it's far enough away that its rays are going to be parallel to anybody that's on the Earth. So you might interpret it as kind of the sun's rays being parallel in this case, whether your ship is down here or up there. The sun is far enough away, it's big enough that the rays can be considered parallel. Stars are so far away, although they're tiny, they're so far away that likewise their rays are parallel. However, the moon is pretty big, and it's also located pretty close to the Earth. So the rays that come from the moon, which are technically reflected from the sun, cannot be considered parallel. And instead, we have something known as parallax. So this parallax means that depending on where you are on the Earth, depending on where your ship is, you're going to see the moon, but it's going to be in a different orientation. And the rays from it not being parallel means that if we were to plot something to the center of the moon, like we do for celestial navigation, we need to account for that non-parallelity, or the parallax that we view in that case. So it's going to be accounted for in the Nautical Almanac earlier in the process of our 5-step celestial navigation process. However, astronomically speaking, it is important to know that rays from the sun and the stars are generally considered parallel to anybody on Earth, whereas rays from the moon are not. The moon also has phases, which don't really phase us too much when we're doing celestial navigation, but it is interesting to note, and astronomically speaking, what's happening is it represents an alignment or a misalignment of the sun, earth, and moon system, a 3-body system. So if the Earth is here relative to the sun, when the moon is on the opposite side of the Earth, you end up with a full moon, fully illuminated, very easy to shoot the lower limb of the moon, no matter where you're at on the surface of the Earth. As the moon moves into a different phase, a different location, only part of it is going to be illuminated. The rest of it will be dark. So relative to the sun, one face of it will be illuminated. Again, usually pretty easy to shoot the lower limb of the sun, but depending on where you're at on the Earth, for example, if you're near the North or South Pole, this same thing might be tilted in a certain way, causing it to be easier or harder to shoot the lower limb of the moon, which is why we often do shoot the upper limb of the moon, depending on its kind of orientation relative to you, wherever you are on Earth. The higher your latitude, the more tilt there's going to be relative to it. When the moon is here, it is obscured, obscuring the sun. It's kind of blocked off, and you're going to end up seeing just the new moon or maybe a tiny little crescent of it. Makes it difficult to observe either during the day or the night. Why don't we have eclipses every 14 days as the moon kind of changes its orbit like this? Well, not only does it, revolve around the Earth, it's tilted in a certain way that makes it pretty rare for these things to line up in such a way that the shadow can impact on Earth. However, eclipses do happen. They're phenomenal. If you ever get a chance to witness a total solar eclipse, it is worth traveling for. It's almost one of those kind of life-changing experiences if you're interested in the sky and that kind of thing. And then finally, as the moon completes its revolution around the Earth, you end up with a different face of it kind of illuminated. I guess we'll represent it the same way as earlier, but it's going to be in a different kind of position relative to the Earth. So at certain times of the month, it's very easy to observe the moon for celestial navigation, including shooting the lower limb of it. At other times, it's a little bit harder. The good news is, for the vast majority of its orbit, the moon is visible, and sometimes it's even visible when the sun is out. So you can get a sun-moon fix during the day. So the moon is a harsh mistress, according to Robert Heinlein's book, but it is an excellent object for celestial navigation if you can deal with the nuances of horizontal parallax and the orbit and the inclinations that come with that. So if you thought solving celestial triangles with HO229 was awesome, there is another way to do it, which may appeal to you as a navigator, or it may not, which is okay. It's the direct calculation method of doing things. So remember when we used HO229, we were solving the triangle to get a computed height and an azimuth angle from that. And when we looked things up in the book, there was some steps and there's some process, but ultimately we're interested in the angle above the horizon as if we were standing at the assumed position and the compass bearing to that, so that in step 5, we can plot it and do something on a human scale chart. This is how the book is calculated. And so if you ever wanted to do this directly, you certainly can. So the sine of the height computed is just going to be equal to the sine of latitude times the sine of declination plus the cosine of the latitude, the cosine of the declination, and the cosine of the LHA. So these are all values that you have anyway from step 3 in our celestial process. If you can apply them this way, you can get the sine of the HC, and then if you just do like sine -1 on each side, you can end up with the HC all by itself. So it's a pretty straightforward process if you have a scientific calculator and a little bit of practice. Likewise, the azimuth angle, the tangent of the azimuth angle is equal to the cosine of the declination times the sine of the LHA, all divided by this massive term, the cosine of the latitude, the sine of the declination, minus the sine of the latitude, the cosine of the declination, and the cosine of the LHA. So not something you need to memorize. Maybe you could get it tattooed on yourself, or you can look up in HO229 the formula if you just want to practice it that way. There are a couple things to note if you're going to do this. If you do the direct calculations, the assumed position can equal your dead reckoning position. So you don't have to go through all that rigmarole of assuming a whole value of latitude, declination, and LHA. You can use fractional values directly into the calculation itself. So therefore your DR could equal your assumed position. It doesn't have to, so you might have some instances where you want to choose a certain assumed position to calculate a triangle, but using the St. Hilaire altitude intercept method with tables means we need to assume a position so that we have whole values to look things up in the table. If you're skipping the tables, you could just use your DR or a position that's close to it, as long as you keep track of where you are and then what you're going to account for relative to that. The other thing to watch out for is that we are using trig in here, and so the signs of things, plus and minus, really do make a difference. So you have to keep track of that as you're kind of working these triangles. Bowditch Volume 2 has an excellent article, which I'll reference in the course. And just through trial and error and practice, you'll kind of get to see where the common sticking points are for these signs. But sometimes if you take a cosine of something versus a sine of something, you end up with a different mathematical sign. Or if you get confused in your calculator, you can easily mess things up and then get your triangle off to the wrong orientation. So I would encourage you to first learn the tables, and then when you feel comfortable in this, start looking at the direct calculations and then see if you like that better. But the tables is probably where I would recommend starting. And then from there, you can explore it or not as you like.